Hello, everybody. This is Jason Montgomery with EE Tech and All About Circuits. First of all, I want to thank you all for your patience here today. There were a few technical issues on the back end of ON24, and we are good to go. Today's session is with Omron and its MOSFET and RF relays for test and measurement applications. And let me introduce Zac Hendrix here in just a moment. But first, I want to say a couple things to everyone that's here in attendance. Some of you might have tried to come to this same webinar a couple of weeks ago. And again, thank you all so much for your patience for the technical difficulties that we had back then as well. If you tried to come to that session and we're waiting around for a session that did never happen, you should have gotten an email from my team and my colleagues as a small token of thank you for sticking with us and coming back here today. If you didn't get that email, which is just a small little Starbucks gift card, please reach out to webinars@eetech.com and we'll get you set up with all of that. So with that, I'm going to hand it over to Zac Hendrix. Zac, welcome. Thanks for coming today.
Thank you very much, Jason. So hi, everyone. I'm Zac Hendrix. I'm the Relay Product Manager for Omron Electronic Components in Americas. I want to thank you all very much for joining this rescheduled event, and I hope this content will give you a strong understanding of the relays Omron has available for the test and measurement industry. So if you do have any questions that are unanswered from my materials, please send them in at the end of the presentation. I'd be happy to answer them for you. So before we begin, I'd like to mention I'll have a few poll questions that'll come up through the slideshow. It would be great if everyone could participate to help me highlight strong information based on that feedback. And to start us off today, I'd like to ask, what brought you to today's webinar? So would that be general interest, the desire to downsize boards with smaller switching options, future projects that can utilize signal relays, or high-frequency switching projects? And if you could just answer this, I'll circle back to the poll results a little bit later, and we can move on from there. All right, today my main focus is going to be to highlight the benefits of our solid-state MOSFET technology and high-frequency electromechanical relays, particularly in the semiconductor test and measurement space. I will also provide a base of knowledge on how to understand the properties of MOSFET relays by discussing the internal structure of these components. I'd then like to move into some important G3VM terms to know and how they're utilized. And from there, we'll move into exploring the relationships between these terms and the product outputs. I'll also briefly overview the range of additional relay products Omron has available and show our latest and greatest product offerings for applications ranging from test signal switching to higher capacity power supply switching of test equipment. This will then lead into the introduction of our new and upcoming modules. That's the T-Module and our single pole double throw MOS module. And then lastly, I'll showcase some of the tools we have readily available by request or on our website that will contribute to selecting the best product to fit your needs. So before we go on to the next slide, I'll switch over. We saw a lot of high frequency and general interest for today's presentation. Luckily, we're going over a lot of things that I just went through on the agenda, RF being a big portion of it at the end, but a lot of different types of products. So hopefully we can narrow down your interest by the end of the presentation. Thank you for answering that poll. So for the slide here, we'll start with basic information on our MOSFETs and ramp up to understanding key characteristics of our newer products. G3VMs are our MOSFET relays, and one of the biggest advantages of a MOSFET is the flat on resistance that it provides due to no mechanical switching components. And this is compared to an electromechanical relay that will experience a gradual rise of contact resistance over the life of the component. So this allows for a much longer life of the product, and we see this in the graphical representation of mechanical life here in the lower left. MOSFETs will provide a lifetime of continuous use of about 7 to 11 years, usually failing to the weakest piece part, which is the LED. And then some other well-known basic product information is the very small size and profile of the MOSFETs that allows for an increase in number of test sites and channels on cards, an increase in tester efficiency, and overall allowing for a lower cost of test. So here we have a view into the internal structure of a MOSFET relay. I want to first point out some of the major piece parts that make up this component. So as I highlight here, firstly, we have the LED, which as I mentioned before is the weakest part of these relays. So they still have an extremely long life and consistent output over that lifetime. The next is the PDA, or the photodiode array, which takes that light input from the LED and works in junction with the MOSFET chip to act like the contact portion of an electromechanical relay. The big importance here is that the LED input and the PDA have total optical isolation. So this provides a very large amount of isolation between input and output of the device. And a good note from the graphics on this slide is that the same componentry is utilized within the smaller packages of our MOSFET lineup. So even while using 2-chip stacking methods for our VSON type and 3-chip stacking methods for our smallest SVSON type, we still have the optical isolation between LED and PDA and the interaction with the MOSFET chip that exists in the largest DIP package. So with the trend of space savings, we see the transition from our older and larger DIP package down to our newest SVSON package. From our DIP type to our SVSON type, there's a reduction in size around 90%. And this small option is comparable to a grain of rice with 2 by 1.45 by 1.65 millimeter dimensions. The lower left here shows board space comparison for different package options. And then by graphical observation, we can see the range of floor space options by using MOSFETs spans from around 32 square millimeters down to less than 3 square millimeters with our SVSON. Another quick basic slide here that will set us up for understanding some details further on into the presentation. As I mentioned, on resistance, notated as R-On, can be directly compared to a contact resistance of a mechanical relay, and that will be flat over the life of the MOSFET. Also, off-state capacitance, or C-off, is the capacitance the device adds to the circuit when in the off state. This can influence the signal transmission and to and from the device under test. Another thing to consider is the off-state leakage current. They will leak some level of current when in the off state. The advantage of Omron MOSFETs over other FET technology is that we're now in the picoamps of leakage, and some of our products even in the femtoamps. So though it does exist, it is very, very low in our products. And then lastly on this slide is the LED forward current, which can be between 2 and 50 milliamps of driving current to the LED. This allows for many more MOSFETs in place of one typical electromechanical or reed relay. And then this brings us to the question, what is C by R? This directly relates to our last slide because here we're talking about our C-off and R-on. And essentially the importance in signal transmission of these values deals with the total harmonic distortion and the impact it will have on the rise time of the passed signal. The C by R is the off-state capacitance multiplied by the on resistance. In a traditional electromechanical relay in a circuit, the ideal signal will have sharp corners and flat edges transmitted through the relay. When introducing a MOSFET relay, clipping can be seen in the signal, showing a delay in the rise time, and this effect is more severe at higher frequency signals. So the lower the C by R, the less delay will be seen in the signal's rise time. Omron has taken notice in this, so as seen below from our website, we call out low combinations of that C by R in our selections. And the biggest contributor to the clipping is the off-state capacitance, but as you can see here, we have a variety of options in the low picofarad capacitance levels to utilize for higher frequency applications. So just a brief touch on the parasitic diode that can be seen in our MOSFET relays datasheets. I just wanted to mention that this diode has no effect on the circuit it's applied to. It simply exists to allow switching of both AC and DC currents. It allows flow in both directions, and all the datasheet ratings take into account the existence of these diodes. This bidirectional switching allows Omron MOSFETs to pull ahead from photocoupler options that can only provide one-way DC switching and phototriacs that are only useful for AC switching. So the total harmonic distortion is directly related to the previous C by R slide. When passing a signal through a traditional electromechanical relay, like I mentioned, you would see no distortion from input to output of the wave. In other switching options that involve phototriacs or photocouplers, large signal transformations can be seen. Omron MOSFET's photodiode array to MOSFET chip connection provides a clean transfer of input to output signal with very good signal linearity, giving it a clear advantage over other types of signal transfer. And as we see noted at the bottom of the slide from a competitor datasheet, using their phototriac product with an input pulse width of less than 10 milliseconds will increase the turn on and turn off time of the device. And here we have two test representations of that THD, the total harmonic distortion, as compared to R-On and C-off levels from different G3VM options. In condition 1, where the relay is connected in series and is closed, we see decreasing R-On values. With decreasing R-On values, we have lower THD in the output. And then for condition 2, where the relay is in parallel and is open or off, we see lower values of C-off values provide lower THD in the output. A good relay that exemplifies a balanced THD value for both conditions is the 21UR10, which we can see at around -85 dB in both plots. And though it may not be evident from a first pass at our datasheet, we do offer the capability to double the load capacity of some of our G3VM series for DC loads. This can be done by taking into account the 3 connections that are mentioned within the datasheets. Connection A, this is the standard connection for AC and DC polarity, both polarity DC loads. Connection B is special for DC loads only. It offers lower on resistance values without an increase in off-state capacitance, but must be used with the specified polarities. And then lastly, the doubled capacity comes with the connection C. It allows even lower on resistance, this time with the sacrifice of gained off-state capacitance. But as it can be seen here at the bottom of the slide, the carry current rating is doubled from 2.5 amps to 5 amps for the example relay. This provides a great option for DC parametric testing or for higher current power supply testing switching up to 10 amps, which is the maximum rating we can achieve with the G3VM series currently. So next we have the relationship between the LED forward current, R-on, and time on and time off. So as I mentioned, the on resistance is flat over the life of the MOSFET relay, but there is some amount of manipulation that can be applied to further decrease this value. By increasing the amount of driving current to the LED up to about 20 milliamps, you get an output similar to the curve on the left side of this page for on resistance. This occurs because the amount of forward current through the LED causes a brighter illumination of the component. And not only will this decrease the R-on, but it will also greatly decrease the turn on time of the relay. So this is just as a brighter flashlight would cause a quicker and stronger reaction from a person or any animal when shined in their eye. The PDA reacts in the same fashion. And then following that, when an optical device or an eye gets hit with a brighter light, the recovery time to return back to the normal state is a bit longer. So this is where there's a slight trade-off for a higher time off than we see, that we do see here on the bottom left graph. And then lastly, on the right side here, I have examples of MOSFET endurance for different LED forward current usages. The maximum advantage gained from a higher forward current will be right around the 20 milliamps that we're looking at here at the second graph. As this is showing continuous time in hours of usage, we can see that stressing the LED to this extent will still provide a much longer lifetime than any electromechanical option. So moving into temperature, I'd like to note that our newer products are maintaining a higher temperature rating of 110 degrees C. And this can be seen in our T-Module, which I'll talk about later, and our smallest package sizes, such as the 21UV, which is VSON, and the 41QR at an even smaller SVSON. That being said, a lot of MOSFETs are being used for automotive test or burn-in boards that are seeing temperatures far in excess than what our products are rated for. Though our relays aren't rated at some of these extreme temperatures, we understand that the backside of these boards where the relays are housed are not seeing the full extent of this heat. So it is definitely applicable. Thinking about temperature rise, it's important to understand the effects on MOSFETs when it experiences more and more heat. So these graphs here relate the leakage current, the trigger current for turning on the relay, and the on resistance that are all increased with temperature. So what is helpful to know is that all of these graphs are very accurate and consistent from part to part for a specific part number. And we have this information available for most of our G3M products if they're required for any high temperature application. Okay, so before I move on to specific product offerings from Omron, I'd like to take another poll to gauge where your interest is for relays. So for this question, I'd like to ask what relay quality is most important for your designs? Is that high temperature, fast switching speed, current capability above 5 amps, high quality signal transmission, or high frequency switching capability? So we'll circle back to this soon. I'm going to keep continuing onward. So the next section will expand on the new technology and future developments in MOSFETs that Omron is moving towards or currently has available. Before moving into more MOSFET products and news, I wanted to point out that Omron has many more relay solutions outside of solid-state relays that are considered very high quality in the marketplace. So if you ever encounter an application or any design that requires an electromechanical relay for a high capacity, we offer products ranging from 2 to 120 amps with many varieties in size and features. If you think you have a need for a product outside of the MOSFET families or the small signal relays, feel free to reach out to us and we'll gladly look to a solution for your needs. So now let's take a look at some of the higher switching current types that would be good fit. Actually, different slide. So now we're back to the MOSFETs in general. So on this graph, we have a good overview of products by electrical capacity and product characteristic groupings. So we can see there's a great deal of categories covered with our MOSFETs with a wide variety of continuous load currents and load voltage capabilities. We do have resources on our website that make it easier to pinpoint a grouping or characteristic that best suits your needs. And I'll make sure to note on a later slide where that information can be found. And this is a slide that I thought we were moving to. So this is taking a look at some of the higher switching current types that would be good fit for power supply switching. The HR series is a great example of reaching these higher currents, maybe even higher by using connection C for DC loads that we went through earlier. This series also has a very low on resistance with values in the low milliohm range. And all of these side-by-side comparisons are available on our website for use if you'd like to look at the multitude of options within each category. And so this is a similar depiction for that high current, just as we saw for the C/R, low C/R slide as well, all on the Omron Components webpage. So our small packages are our VSON and SVSON packages. And over the years, we have looked to improve two main things that were less optimal with past products. Those are solderability and the ability to access a probe point on the relay for testing if need be. So this is why our smaller package MOSFETs were designed with these cavities in red that allow more surface area for solder connections and also points for probe testing consideration. This provides an additional solder relay shear strength of over 95 newtons with the testing conditions outlined here in the lower right. This low profile and high strength solder design provides a much more secure connection to the board than most competitors that have either taller relays or less terminal surface area. I'd also like to draw attention to the note here at the bottom of the slide. As Omron has released more and more MOSFET products, the trend has been to both reduce size and offer many options for different features within each package size class. This allows for a copy exact design nature, as there's no need to change footprint or dimension with the vast variety of models in each package size. So just real quick before I go into these products, the last poll, it looks like we had a lot of members here for high frequency switching capabilities, which is great. Later on, I'll go through our RF relays and the range of options that we can support. Also high quality signal transfer, which MOSFETs are ideal for with our low C by R types. So it's flipping on its own. So please stay tuned and we can find a product for your needs. So yes, so now we're moving into specific relay products, starting with our G3VM QV series, which is the latest voltage-driven models in an SVSON-L package. These products provide a range of options for designs looking to drive relays like the coil of an electromechanical relay. Instead of current driving an LED, these currents are voltage-driven. These relays are voltage-driven. So the SVSON-L package includes the built-in current limiting resistor for voltage driving, while still saving space being the smallest package size offered. This eases design efforts by eliminating the need to consider a current limiting resistor within the input circuit. And to accommodate more driving voltages, Omron has released a 5-volt high and a 2.5-volt low for each load voltage type. So with this NPI, Omron has released 5 different models. 31QVH and 31QVL are 30-volt load products. The H symbolizes that high 5-volt input voltage, and the L symbolizes low 2.5 input voltage. Next are the 61QV2H and QV2L, 2 levels of input voltage for up to 60-volt loads. And lastly, the 61QVH. This is another 60-volt load product and operates at a 5-volt input, but it stands apart with a low offset capacitance rating of 20 picofarads maximum. And all of these products meet the 110 degrees C temperature standard. Here we do see the design differences by using the SVSON-L type. Previously, PCB design required an external current limiting resistor to drive the MOSFETs by voltage. With the inclusion of this SVSON-L package, extra design effort can be eliminated to add this resistor. This saves time, space, and money for the user. On this slide, we have the proposed test applications for Omron's QV series. The main benefit here being the ability for improved high-density relay mounting. And some typical applications would be power supply switching for test equipment, as we see low leakage current combined with higher current switching capabilities. Also, test signal switching is also a target for the ease in design, and small size can provide a valuable addition at these low levels of leakage and on resistance. And then lastly, we see the potential in DC measurement switching, which may require lower offstate capacitance. And this is where we see the most value in Omron's low C-off type, which is that G3VM 61QVH. Next, we'll dive into the latest MOSFET release, which is the G3VM WR series. This is an all-new PSON package type. And this series was just released this March and targets high current applications within smaller packages than its predecessors. So the PSON package, or Power Small Outline package, showcases an entirely new shape and terminal pad style than previous packages. This expansion of the terminal improves heat radiation performance. Also, the PSON terminal shape provides an inlet for improved solder joints and visibility. Another benefit to this release is the 500-piece tape and reel packing, allowing a smaller master pack quantity for orders. When taking a look into the specification features of the WR series, we see the high currents that are attainable within the small 3.4 by 2.1 by 1.3 millimeter package size. The 31WR or the 30 load voltage model, is able to withstand a high 4.5 amp continuous current with a 10 amp pulse-on inrush. The 60 volt option is rated at 3 amp continuous current with a 9 amp inrush. And lastly, we have released a 100 volt choice that can withstand 2 amp continuous currents with a 6 amp inrush. Again, all of these electrical ratings at that 110 degrees Celsius marker. This package is called a power small outline package due to the current levels it can reach in comparison to older products. Omron's existing SOP4 package is larger than the PSON, but its high capacity 60 volt model, which is the 61GR2, peaks at 1.7 continuous currents. Just in terms of the new 61WR, we can see a significant decrease in size with a 1.3 amp improvement in current capacity. And as for applications for this product, we would again look to power supply switching with the higher current capabilities of the WR relays. Overall, it's a great selection for saving space when switching loads between 2 and 4.5 amps. So now we'll switch over and take a look at MOSFET modules that Omron has to offer, starting with our SPDT MOS modules that were released in 2019. We're now offering 3 packages, our 60 volt package and 2 20 volt packages, M10 being our low C-off model and M11 being our low R-On model. For this product, we work toward a package for a single pole double throw option with a footprint that is the same across all 3 models, allowing for that copy exact design that I mentioned before. So the goal is to continue this design growth to allow more options and versatility. But as it stands now, these are the 3 characteristic models that we have available to you. So M10 type not only offers the low off-state capacitance, but provides good quality isolation and insertion loss outputs, while the M11 provides low on resistance coupled with a higher load current capability of up to 1 amp. Again, here are the key features from these SPDT modules. We have our traditional MOSFETs packaged together to provide the double throw option. They provide a long lifetime. The package size provides space savings from an electromechanical SPDT option. They allow for copy exact design with different characteristic variations, and they are operated with 5 VDC input and contribute to an overall increase in design efficiency. Here's a side-by-side in specs for comparison. In blue, we have highlighted the main features of each product. So the 66M has the 60 volt capability, 26M10 is rated to that 1 picofarad C-off, and 26M11 has the 1 amp load current capability with 0.21 ohms of on resistance. It's also important to note that all 3 of these modules have a low leakage current of 2 nanoamperes or less. And just for a quick point of reference, this is a look at a potential circuit redesign to replace a traditional single pole double throw electromechanical or read relay option with the SPDT MOS module. Due to the parasitic diode that I mentioned earlier, we can also see the added benefit for bidirectional DC and AC switching. And Omron's next product to note is the T-Module, or our T-Switch module. We have released the 20 volt version of this product, which is the G3VM 21MT, and we have plans to release the 60 volt and 100 volt versions very soon within 2021. As these 2 versions will be the, part of our next new release for relays, I do have evaluation boards for both products on hand. If you think you have a project that could utilize this type of relay, please reach out to me and I can provide them to you for evaluation. So to start, the T-switch is a known circuit that exists for a lot of semiconductor test cards, and so the goal was to make to take multiple MOSFET components and consolidate into one to allow that extremely low leakage current and high isolation. So inside this one package are 3 discrete MOSFETs and additional components to create the circuit shown. 2 in the open state to the device under test, the DUT, and 1 to the ground that is closed, controlled by internal gates. Any noise in the circuit will be drained to ground, allowing that high isolation between input and output to the DUT. So the T-Module design provides virtually no leakage current. It is rated in the low picoamperage, but as test data will show, the values are actually in the low femtoamps of leakage. This capability is offered in a very small package for space savings and still provides the long life of all other MOSFET products, and then much higher than reed relay and electromechanical relays. These traits will also be seen in our upcoming 60 and 100 volt versions as well. And moving into those two upcoming versions, here's a look at the specs that will be offered by these products. The 60 volt model will have a higher amperage rating of 800 milliamps, and the 100 volt version has the benefit of high load voltage. As the second column of this table indicates, Omron set strong targets to meet for this new product, and they were all met, some by a great deal. I'll take a quick pause here. There's a good deal of information, so I'll let you eye over what you deem most valuable specs for your needs. So this next slide takes a deeper look into the isolation and insertion loss performance of the T-Module. For isolation, we have less than 20 dB around 1.5 gigahertz. And so we're now able to take the MOSFET technology and get out of the megahertz and push into that gigahertz range. So this is a huge advantage for our MOSFET technology to reach these higher frequency signals. And as for leakage current, we rate our T-Module in the picoamperage range, but from actual test data, we can see much lower results. Many values appear that are even under 100 femtoamps. This was the primary goal of our T-switch module, to be able to have that low leakage that is very comparable to that of mechanical relays. So again, before I move on, if you have any additional questions or would like more information or evaluation boards, please reach out and I'll gladly provide you with answers and additional resources. I would also like to note we have a newly developed comparison data book that shows the test data from each version of the T-Module, as well as outputs from reed relays and discrete MOSFETs. This is great to see the performance of T-Module versus predecessors in terms of output. This is available upon request as well, so just let me know. And then finishing up MOSFET talk, I'd like to point out that we do have a good deal of resources available on our website to best choose the relay that is right for any given application. So within the sales and technical support page, we have a download of this G3VM MOSFET Relays PDF that provides all of the information necessary in understanding how to pick a product. And then once this PDF is referenced, you can move to the relay search portion of our website and enter in the part number in question to have a look at the detailed datasheet. Also, near that datasheet link, you can access the solutions PDF for MOSFETs. This document shows potential failures that could occur with G3VMs and what preventative measures Omron recommends to avoid these failures. So the Excel file excerpt shown on this page is another resource available upon request. While it's not on our website, I can provide a standalone file that will make it easier to sort through the G3VM groupings with different characteristics by simple filtering. So this resource is also available to download in the resource box on this page. All right, so we've reached our third poll, and this directly relates to our next section. So for RF applications, what frequency is most relevant to your project? So that's you do not work with high frequency applications, 1 gigahertz, 3 gigahertz, 8 gigs, or 10 plus gigahertz. Okay, so that poll leads us into our last topic on the agenda, which is Omron's G6K RF relay. This is our electromechanical high-frequency relay series. Our standard RF relay, it's not moving, there we go. So our standard RF relay has been around for quite some time and was followed up with the S version, which is mainly a space-saving version for increased density boards, and then expanded even further to our -T version, which is a 3 gigahertz rated relay with performance graphs all the way out to 6 gigahertz. I'm going to give you guys another moment here to look through the plots for isolation and insertion loss before we go on to the next slide, just to have an idea of what kind of applications you've encountered that these relays might be suited for. I'd also like to note that we do have S parameter files for simulation upon request. So just let anyone on the OMRON team know, or myself. And just for the last poll, it looks like 3 gigahertz was the sweet spot. We have a lot of members here interested in that range. So as I just mentioned, this type of relay would be perfect. We have between 3 and 6 gigahertz of performance, 3 gigahertz being the rated performance, what we spec it to. So if you would like to dive deeper into these products, let me know. There's white papers available, and we can take a deeper dive after this presentation. So next we have the expansion into our -V version. This version is a double pole, double throw relay intended for high-speed digital differential circuits. It has great insertion loss and isolation performance as seen in the table and is applicable for frequencies up to 8 gigahertz. All of this in an extremely small package. Again, for performance, we have graphs here to show the data for insertion loss and isolation if you'd like to take a look at these as well. And then also on the right side of this slide, we have the eye diagrams for different data rates, offering a very clean signal all the way up to 12.5 gigabits per second. All of these features making it an ideal option for high-speed differential circuits. So the added value of the design of the -V version is the good linearity, but also competitor Teledyne relays were taken into consideration for the creation of this product. Since crossing circuit paths would cause interference in the target application, Omron's 8 gigahertz G6K relay was designed to allow for an ease in setting the transmission line close to the terminal mounting pad. With this design allowance, impedance mismatch can be avoided by following the simple layout depicted here at the bottom of the slide. So that's my content here. Thank you all for taking the time to learn about Omron's relay offerings for test and measurement space. If you'd like to stay in touch with Omron electronic components, please feel free to stop by our website, components.omron.com, where you can stay in the know by signing up for our monthly new product newsletter. If you have any questions or comments for us, please feel free to send an email to components@omron.com or to myself, and a member of the team will gladly assist you with your inquiry. And then lastly, I'd like to encourage you to follow our LinkedIn and YouTube accounts for the latest company and product information. And that brings us to the end of my presentation. But before we move on to the QA portion, please note my email on this slide for any additional conversations you may want to have following this webinar. I'm also going to jump to one final poll question that I'd really appreciate your final input on. So what product from today's presentation most interests you? The G3VM QV voltage-driven type, the G3VM WR high-power PSON type, SPDT MOS module, the T-Module, or the G6K RF type. And with that, I have no more follow-up questions for the poll. This is just for my information to go back, so I'm going to hand it back to Jason for Q&A. Thanks a lot, everybody.
Great, thank you, Zach. Can you hear me okay?
I can, yes.
Perfect. Yeah, Zach, I want to thank you for that really thorough and interesting presentation. I know we've got some good engagement here. A couple notes for everyone who's in attendance here in the audience. There's a Q&A box that you've got on your screen. There's a Q&A widget that you can use to submit questions as we're going through some of these other ones that have come in as well. So definitely this is a great time. We've got a little bit of time and we're happy to go through those questions. And I'll also note to everyone that's here in attendance that there is a resource area, kind of a resource box that you've got on your screen as well. And Zach and Omron wanted to make sure that we pointed those out, and please take advantage of that stuff that's there as well. So with that, Zach, I think we can start jumping into some of the questions I'm seeing here. First question is, are 1, Form A, and C the only contact form options for the G3VM relays?
No, actually. So just as we do for our mechanical relay lineup, for the G3VMs, we also have 1 Form B, 2 Form A, and 2 Form B models in that family, on top of what we already discussed in this presentation. And if you need one of these for your design, on our website, we do have the ability to filter the form factor in the parametric product search. So if you want to visit the website, you can see all the different types of form factors available.
Got it. Thank you, Zach. Next question that I'm seeing here, do the MOSFETs have 3D CAD models out there?
Yes, they do. So also on our website, so Omron Electronic Components website, that's components.omron.com. If you search for a specific relay, you will be able to see a CAD tab to access both 2D and 3D files, and that'll be right next to the datasheet tab when you search.
Got it. Thank you very much. What about resources out there to learn more about the T-switch relay? Yes.
So as I mentioned, we have the 60 volt and 100 volt versions coming out soon, and with that release, I'm sure you'll see some information about the new products going out to the media. So also, currently, we have a video on our YouTube page, Omron Electronic Components YouTube page. And this video, it has a product overview of the G3VM 21MT, which is the 20 volt version. So if you want to view that, there's also a PDF available for the T-Module that you can find on Omron's website. So a lot of resources, or you could just reach out to me and I can send them over to you as well.
Sounds good. Another question that I'm seeing here, can you please go over what effects temperature has on MOSFET relays again?
Yeah, okay. So there's a lot that temperature does do to the MOSFETs upon application. An increase in temperature can cause a rise in the on resistance, a rise in the amount of forward trigger current required to drive or to activate the relay, and also a rise in leakage current. So by increasing the driving current to near that 20 milliamps that I talked about in the presentation, you shouldn't have to worry about that forward trigger current value, and also your on resistance will be reduced at the same time. The leakage current is the only remaining factor, and it's important to look at the graphs for temperature versus leakage current for the part number in question to find out what you would expect in your own design.
All right, thank you, Zach. Next question that I'm seeing here, are the G6K RF relays, is that the only option for high frequency applications?
Okay, that's a good question. So it would really depend on the application, but the short answer is no. Our MOSFETs have capabilities up to 900 megahertz for clean signal transfer. And I briefly touched on it in the presentation, but the T-Module provides quality performance up to 1.5 gigahertz. So with that in mind, there are options within G3VM portfolio depending on the design as well.
All right, sounds good. Next question, does the T-Module have any references for proper board layout?
Yes, absolutely. So for the T-Module, we do have multiple resources that can be referenced for proposed circuit design. as well as the details on input control circuit, since this is a brand new product. The easiest resource to access is the G3VM21MT datasheet, and we'll also see this with the addition of the upcoming 60 and 100 volt types. As well, we have the comparison test data that I mentioned available upon request that has even more detailed information on circuit design and best use practices for the T-Module.
Got it. Thanks, Zach. Another question here that I'm seeing is about data sheets. Is the information on the data sheets for the G3 VMS, does that contain everything you need to use them?
Our data sheets are very expensive. They contain a lot of output graphs based on different use conditions, but I wouldn't say all of the information is located there, as there's so many specific requirements depending on the application. There might be some data that you find lacking, but we're open to running additional testing based on your needs and may even have those materials on hand for reference. It'll really depend on what's being sought after, but don't be afraid to ask because we'll look into it for you.
Sounds good. Another question here. If the MOSFET can be driven with higher current to improve the turn-on time and resistance, why wouldn't you just use the maximum value of current?
Okay, that's fair. We do see an improvement in both the turn-on time and R-On, but it's also important to keep in mind that there's some trade-off. Firstly, being the amount of power required to drive the relay, it may be unnecessary to drive with additional current if the output you're gaining isn't substantial. And secondly, the higher the forward current, the lower the life of the LED and the relay itself. You're also going to see an increase in the time off of the device, as I mentioned earlier. So it's good to follow the recommended driving current or to find the sweet spot that makes sense for the design based on our output graphs.
Understood. Yeah, I know those trade-offs are important to take into consideration for sure. Another question, can I contact Zac to receive the Excel selector guide for the G3VM?
Yeah, you absolutely can. I'd be happy to provide it. You could also reach out to the Omron representative in your area, the sales member. If they do not have the most updated version on hand, I'll make sure they forward it on to you. But please feel free to send us an email.
Perfect. Sounds good. Another question I'm seeing here, does Omron provide S-parameter models of your T-Module?
Yes, we can provide that. So we will have that available for the upcoming and the current model. So please reach out and we can talk about your application and we can get you the S-parameter file as well as other files that are required for evaluation of the T-Module.
Perfect. And then this is a kind of question we see quite a bit. Are you planning any high temperature relays to some more automotive products validation, specifically up to 150 degrees Celsius?
Okay, that's also a great question. So we fully realize that there are a lot of automotive tests that do require 125, 150 degrees C ratings. We are looking into the potential of moving towards development of a new product. We don't have anything available now, but if you could send me some requirements for your design, that would be great in researching for that development, because we'd love to bring to market something that could be a solution for that.
Perfect. And we're through the queue that we've got right now, Zach, so I'll give everyone in the audience another couple minutes if they want to submit anything else. It's been some really good engagement there. And yeah, I will, I'll mention a couple things here while we might be getting close to wrapping up. Zach, I know that you are very eminently reachable and want to be in touch with the people who are here in this session. So definitely reach out to Zach in the email address that you're seeing on your screen there. And I know he'll be happy to continue these conversations offline as well. One other thing I'll mention just briefly is that there on July 15th, there will also be another webinar that I'll be moderating with Omron as well, and we'd love for people to sign up and join us for that one as well. You can find the information on registering for that on All About Circuits webinar section. Yeah. So Zach, is there anything else on your mind or anything else you're wanting to reemphasize, close us out with, or anything like that?
Not too much, Jason. I really want to thank you and EE Tech, and a big thank you again to all the attendees who were able to join the rescheduled event. We're really happy you could join, and if you'd like to keep talking offline, like Jason mentioned, I'm really eager to have a chat with you on your projects. And thank you very much. You guys have a good day.
Great, thank you all very much. I've been Jason Montgomery with EE Tech and All About Circuits, and we thank everyone for hanging in there with us for this session, and really glad that we've been able to get this information out to you today. Definitely go and check out that webinar that's coming up on the 15th of July as well. We'll make sure to drop a link for that registration in kind of the post thank you for this as well. So thanks everyone who joined us here today, and we look forward to seeing you at another live session sometime soon.